All yours.
Okay, didn't even notice the time. Good morning, everybody. Hi there. Thank you all for joining. So today, a little bit like that, and if it would work, it would be great, and if it does, it's fine. So I'm just gonna first of all recap on the reconstructing of the head that did last time. Um, yeah, second. So today I will do a recap on the reconcile and try to break it down a bit more. I think it would be good if there would be any question or something that's not clear. And then I will try to show the opposite way of how cut to track basically try to find the point, um, or what it is actually the value that you're trying to put in. Yeah, cool. So last time we talked about how to reconcile. Basically, to reconcile is just to project a point. I think the name is a bit confusing, but last time we talked about how we want to try to project a point from 3D space into to the screen, right? I think that was the point. And we started with basically trying to zero everything out, trying to cancel everything out, right? So I basically said, let's put the camera in 0, 0, no orientation, and our x is going to be on the -1, which basically represents for us um, 1 unit, which is basically a representation of the image plane or the sensor, where it would fit, where would it fit. And we use the aperture of basically 1 and focal length of 1, which basically means it doesn't have any effect on us, and resolution of 1000. So this basically kind of like eliminates everything first, then we can build up again the steps of to see what we actually need to make it work. Um, I started by actually saying, so if I put a card that is 1 unit away and it's basically 1 unit size, we saw how it's basically aligned with the obviously FOV, or basically the focal layer length that we have over here of the camera. I have an axis in the center. And I started by saying that the offset, we start with it because our 3D system actually is in the center of the camera. And in 2D, the center of the image is actually over here at the bottom.
Can you share the screen?
Am I not showing my screen?
Oh, is it me?
No, the screen is shared.
It's shared?
You need to set up your layout. Yeah.
Okay.
Guys, everyone can see what he's sharing, correct? It's not only me.
Yes. Yeah,
Okay.
yeah.
All good. All good.
Okay.
Yeah. Thanks.
I can see it as well.
Okay. Let's keep going.
So basically, we just said that I zeroed everything out, so it wouldn't have any effect, and then I would basically add everything up. So I'm just going to take like 20 minutes again to reiterate what we've done, and if there is any questions, will be a good time for that as well. So I started by saying basically the first thing is, notice that we have an offset from a 3D to the 2D system. So in our 3D system, our origin is in the center of our screen. And in 2D, our origin is actually in the coordinate bottom. So that's the first thing we have to accommodate for. But then I thought about it actually, and I thought it was a bit confusing when I tried to explain it. So I thought that we can do something else. And I don't know how many of you are using that, but if you will go to if I open the camera tab and projection, I don't know how many of you are using the Windows Scan and Windows Translate. That means that I can actually translate everything and it would keep everything as if we have a bigger sensor, or basically we have a bigger render and we're just shifting the data or scaling. So if I press over here 1 and 1, you will see it's actually shifting the image. And I thought maybe that could be a good way to, oh, sorry, something probably moved, yeah. To kind of like, first of all, cancel for us the offset and do everything else and then add the offset, because I thought the offset is a bit confusing. It's kind of showing how we're actually using all the other scale kind of like multiplication thing. If you ever wonder, if you can look at the camera and how it looks like, this is our fast frame, and if I would just put 1 and 1 over here, you can see actually how it's actually distorting that, how it's actually shifting all the lines. And that's how it's doing that. So for us, it's kind of convenient to first look at it. And what I want to show you, I think is this one here, is that when we have 1 unit away and basically a focal length of 1 and aperture of 1, By the way, someone told me the other day that you can actually zoom in as well. If you need to see bigger the text, you can actually zoom on chat as well. I didn't know that. If you need to see some of the text that I'm using over here. But we notice that if we have a focal length of 1, then 1 unit away from on the x and 1 unit away on the y exactly correspond to the corner top. 0, 0 for us is now actually the bottom. It's exactly like to the layer, so it's easy for us to see. And I want to say that this is again like a normalized system. If I put just 1 unit away up and on the right, it's basically the 1 over here is corresponding to the width on the x, and the y on the y basically correspond to the height of the image. And if I'll go and change, of course, the resolution, and say I'll use a different resolution, it still works, right? It's basically always kind of like, it's a scale factor. So first thing that we need to notice is basically a scale factor is our output resolution. That's what we started with. And because it's exactly 1-on-1 with basically aperture and focal length of 1, the first thing that we have to do is basically just take the resolution into account. That's what we said. I'll put it back on 1000. And 1 second, sorry, it's not that one. Okay. And I showed how to do it. I said that basically I'll zoom in so we can see the text. To do that, I said that basically we have to link the axis x into our translation and the y as well. Then all we have to do, because our axis is now 0 to 1 and 0 to 1, we just have to multiply it with the height and width, right? And that's what I'm going to do over here. I'm going to go and I'm going to multiply them with width and with the height. Okay? And now it's actually aligned to the axis. And if you have to see what I'm writing is actually, I'm just writing the axis, translate.x, x translate.y, then multiply with the height and with the width. And if I'll go and move the axis, and I'll open this one as well. So this is kind of like working for us, right? We have this scaling factor. That's great. The second scaling factor that we had is, again, is basically this guy. It's the focal length and the aperture. And I'll put it back on 1. Actually, no, I'll put it on 10. Still actually a good thing to see. And we can see as we are basically changing the focal length, this case is actually 0.5. It's exactly at the middle between where it was. And if we put it on 2, it's times 2. So it's another just scaling factor. That's all it is, right? But we also know that it doesn't work alone. It takes the aperture as well. So if I'll do over here 2, it's actually divided by half. And if I'll do half over here, it will multiply it, right? So we have a ratio between them. And I show that basically it's a ratio of triangle. Right? I'll just show it quickly. I think it's somewhere over here. I just showed it's basically this ratio of, this is our image, right? And we have this aperture value. We have it over here. So basically we have this triangle, which is a camera from above, let's say, and I'll split it in half. And this half line over here, exactly this guy, is the focal length. So how much it is, basically the length of it. And this aperture is corresponding to this guy, basically. Yeah, those are the values over here that we have. And dividing them, so dividing this with this, give us a ratio, which actually tells us how much the angle is changing. So but that's what we're basically using. As we are getting closer and we're making the focal length shorter or longer, we're making this ratio actually bigger or wider or narrow. So this is basically our second scaling factor that we set. And to do that, I have to probably zoom in to see that properly, right? We'll have to write it over here so we can see it as well. I'm taking the focal of the camera, and I'm taking the aperture of it, and I'm dividing between them to get a ratio, right? So now if I'll actually add it as well as a scaling factor, and yeah, it's already here, sorry. I think it's not, it's actually, it's over here. Let's do it again. I had a scaling factor, which I called length ratio. enhance ratio here. And now this is our equation. We have the x time width times the ratio that we just measured and the y height and the ratio. So basically we have two scaling factors. And if I'll go over here and I will change our factor as well over here. Yep, it's also affecting our 2D, so this is great as well. Great, so this is working. And I try to explain that basically we have these two scaling factor that kind of like makes sense. Because what we're doing is kind of like trying to find what's the ratio of change between our 2D image and our 3D image, or our 3D scene basically, or 3D units. So in the 3D units, we have kind of like millimeters and basically meter kind of like measurement. And in our 2D world, it's pixels. So it's not the same kind of like measurements units. And that's why we have kind of like two scaling factor. And kind of like one is putting it in the 0 to 1, as we see like the axis is now moving between 0 and 1, and the other one is kind of like scaling back into the resolution. So it's kind of like this way to kind of like normalize and put everything in the right place. So it's one scaling factor for the 3D system and one scaling factor for the 2D system. And that's why we have those two. And I also mentioned, and I think it was also a confusion last time, that if we have resolution that is not square like in this scale, so let's say like that, we cannot just actually multiply it with the height over here, because Nuke doesn't care about the aperture. Sorry, the vertical aperture. It only cares about the horizontal aperture. One of the best way to see it actually is if I open this guy. Yeah. And I'll look at it. You can see now they have this kind of like different ratio between them. They're not in the same place. And if I'll go and change in the equation in the width and height, instead of on the y as well. Sorry, and of course it doesn't work right now because what did I change? A second. Oh yeah, now it is working. Okay, yeah, I know why it's working. It's not working because we had the offset of the camera over here. So right now it's kind of like off. But I want to show that this dotted line is what we're getting from the scan line. And I just actually reformatted, I just fitted everything to be exactly the width is now, the height is exactly the same as the width. And I want to show you how now it's aligned. So if I go and ask the F to be 1-on-1, which now I don't get the right result because now I clearly did something wrong. What did I change? One. Yeah. Okay. So now we have again the camera is on 1-on-1, just the same thing. We have an axis, and I just want to show that 1 on the Y now is outside. And if I had the height to be the same as the same size, we can see now it's actually lining. So it's only cared basically about the horizontal aperture, which drives everything for it. So we have to always think in that kind of like width size that we have in all of directions. If I go and put 0 over here, 0, it will be at the bottom as well. But clearly our 0 actually starts over here. So that's why we have to do this width and width time over here, as we said. So we just said we have the different resolution, the height, focal, and now we have to add, of course, Z. I'm going through it quite quickly because we've already been to that, but if you want to go slower or if you have questions, just pause me because then I'm going to add it to another thing. Then we mentioned that we have to, of course, add the Z component, and if I'll go from -1 in the Z and 2 -2, we can see it's exactly half of it, basically. So clearly there is another multiplication kind of like error that we have to take into account. And we said it's quite easy. All we have to do is just divide each component of the X and Y separately with the Z. That will basically, again, put the same kind of like ratio. It will compensate for that. So in order to do that, we already have this kind of like width and focal over here. So now all we have to add is now divide it with the Z. And that's that. I haven't ruined everything. Have I ruined anything? I have. of course, sorry, minus Z. Always forget about that. And it's minus because our image plane is actually flipped. It's in front of us and not behind us like the sensor would be. Okay, so it's minus over here. And now if I go and put 2 over here, it corresponds to our 2D point as well, and it's working, right? So now we have all those factors working. We have the Z, we have the resolution and the focal, and plane basically kind of like all correspond as a kind of like scaling factor, and it's working for our point. Now, of course, we have to add again the offset because clearly we're not rendering like that. So I'm going to cancel again the window translation, put it from 0 to 0. Okay. It means that everything is still on the same ratio. It just means that now we shifted everything to where we used to be, which our origin is actually the center. So now we have to shift everything by half of the width and half of the height to be in the same place, right? Because we offset that. That's all I'm going to do over here. In the end, I'm going to just do width, half of it. So half the size of the width, and then the height. Great. And now we edit the offset again, and we have something that's working. Cool. So 0, 0, still working, and everything is great. And we do minus. Cool. Didn't care about the reconcile so much, I think, but it's working for us. One thing that I think Alexei mentioned, and I think it was a good point, maybe to pause and expand a bit. So the next step, so now that we have basically everything working except the camera, right? We have different Z, we have the focal, different focal plane, and we have different resolution, everything is working, that's great. Now we have to add the camera, of course, and we have all the components. And I expect to do that, we actually have to reverse the camera. Alexei mentioned, asked me if I could do it a bit slower this time, so I can actually show you how I'm doing that as well. Without any special tricks or without any special tools for that. So let's say I have, so to do this example, just to show it in a bit more kind of like in an advanced way, I have this basically camera that rotates around the sphere. And I did it specifically with the camera and with an axis. That's basically two different elements, two different kind of like controllers to the camera. It's not just a camera that we have to flip. The thing is like that. I have sphere in the center. I put the axis we want to find over here on the sphere. And that's what we want to find the reconcile wall. And I place the camera away, actually like that. Then I have an axis that all it's doing is just rotating it in space. So it's actually looking like that. And I hope you can see that. Yeah. I hope you can all see that as well. Okay. So in order to do this reverse, I'll do it now live with everybody. So all good, I'm just copying it as it is. Okay. And reverse order, no matter how much X is over here, we have to reverse the order of them first of all. Okay. So what I mean by that is basically I'll unplug it over here and I'll just reverse the order. Okay. So now the camera is on top. If I have another X over here, just as an example, I will do 1, 2, 3. Okay. I'm just swapping everything. Okay. That's the first step. Then the second step, connect them, of course, is just to flip all of it. And when I'm saying to flip, is to negate the value. It means to put minus on whatever it is. So minus become plus, plus become minus. In this case, our camera only have 6 over here in the translation. So we'll put minus over here instead. And then in the axis, we have to do the same thing. So we don't have any translation, so it's fine. But then I have to negate all those guys as well, the rotation. So I'm going to go and put minus in the beginning. It will negate it. This one have a keyframe, so I have to do it over here. I'll just do curve like minus before. It will keep the animation, but put a minus before it. And of course, I will also have to flip the order of rotation because it's important. So in this case, it's literally flipping the letters. ZXY becomes YXZ. I literally just flip the order of the letters as well. So instead of ZXY, I have to find the YXZ, which is this guy. That's all it is. We just reverse the order of the entire camera movement over here. And it also works with every different kind of like scale factors and whatever it is. You can actually combine all of it, just negate them. Remember to flip the order of the rotation and flip the axis order. And that would actually give you the inverse of that basic camera movement. And what it would look like in this way, actually, to do it like that. So what I've done, I copied the same camera from here, but remove any animations. Now it's 0, 0. The only reason I copied that is I wanted to have the same kind of like focal length. Okay, if you have an animation or whatever, you have to see that. And I plugged this guy that we just did over here, and I let it drive our animation, our sphere, and that's what we want to find. Okay, so basically the entire scene. And now it would actually look like that. So our camera is 0, 0, and now it pushes everything over here. And if we look from here, we can see that actually the sphere is now rotating instead of the camera. Now, if we look from the camera view, we see exactly the same image. This is actually the sphere moving, and this is the camera moving. There is no difference at all between them. Okay? This technique just means that the camera is being cancelled. So it's very convenient for us now to solve the reconcile and to find the points. And when we're doing that, we get actually a point that kind of like rotates over here, and this is our axis, and now we can actually extract what we need. To see that, and I explained in the session about matrices, and if you go to world matrix indexes, the last column over here basically corresponds to our global movement. So if we concatenate a different movement, we'll just look over there. And then instead of now, if you look at the expression, now I said translate.x and translate.y and translate.z. Instead, now we're actually going to go to world matrix, and I'll correspond to those columns. So 3 is actually the last column on the top row, and then 7 is the second row, and then 11 is the third row. So it's basically X, Y, and Z. Doing the same thing now essentially just gives us, you can even see the, I don't know if you can actually see, you can probably even see the curve of the animation. So it corresponds to basically this movement that works for us. And that's what I explained last time. Is there any question, something that didn't doesn't make any sense, or I maybe skimmed over that you want to ask?
So now it's linked to the axis 14. Can you zoom in to see which one is the axis 14 in the
About this guy?
Yes.
Yeah, I'm taking this guy.
Okay. So what would happen if below the scene node that you have there, you put a transform geo and link it
like that? I mean, yeah, I thought about it as well. The thing is, you will not be able to see the world matrix is only per object over here. That's the thing. So we need this. If I will put it over here, it would not. We don't see it over here. It would not change. We don't know.
I see, but this transform geo doesn't have this world matrix instead, or would
no, it doesn't. First of all, it doesn't have it because again, it's per axis, but also it will not tell us where this guy is. First of all, if I'll just put it over here, as I said, it would work actually. We still get the right result. It still actually moves everything for us from the center over here. So it works. The only thing is, and you can see, we get the same result. It's working for us. The only thing is that we cannot see this result where it is. You can see over here, I don't know if you can see, it's too strong, probably, but it's only have the local place.
I see.
We want to see where it is in global. To do that, to see those values, we have to basically put it like that.
I see.
And to concatenate. That's the only reason we're doing it like that.
Okay.
Does that make sense?
Yeah.
Cool. Anything else? Something doesn't make any sense, please don't be shy.
I have a question. You did add this camera 12, and I think that we can just use the original camera and just to reverse it.
No. The original, no, so so last time I mentioned that a lot of the time when I work, I actually like to break those things into two things. One, I like to have an axis and drive the animation over here. And two, I like to have those definition of the internal camera, intrinsic camera, kind of like parameters separately. And that's the reason, because this camera already have translation over here. I don't know if you can see it. They have kind of like a body of 6 pushing in the back. I cannot put it over here. I don't need to reverse it. I don't need anything. It literally needs to be at the 0, 0 because you want to cancel everything, right? You want to be exactly the origin. No orientation, nothing. But I want to keep all the intrinsic things. So focal length, aperture, if I have any scale or translation, that's what I want to keep. So in the real world, I would actually copy them. And I would copy them, and then I would basically zero everything out over here, or basically make it like a default kind of like camera at the origin, and keep all the animation and definitions over here as is.
Yeah, I don't understand. I just was thinking that if you're keeping original camera, just connecting your axis of your original camera to your reverse axes, it should kind
Ah,
of.
and well, we're kind of like doubling up the camera move.
But if you will,
No, yeah, exactly.
it will not.
Sorry, you mean I don't know. It's with the movement. Yeah, yeah.
Yeah, yeah, it's is it so it stops working or it's the same result?
Well, actually, I have to copy the entire thing, I think, to make it work. Sorry, probably. So I would have to do something like that. Yeah, that would work. So if I now copy the original,
Yeah,
it's a bit
exactly.
confusing, right?
Yeah,
If I would copy exactly as the original one, that should
yeah,
also work.
yeah,
But it means also,
yeah.
actually, yeah, we don't care. I mean, honestly, we don't care because I don't even use this result. This is only to show that I only care about this. I only want to see how the axis is translated. This is just to show you
Mm-hmm.
that canceling the camera
Mm-hmm.
now, it's just to show that actually we're canceling the camera. It's 0, 0.
Yeah, yeah, yeah. I completely understand that. It's just something that I think what is quite clear if we keeping the original camera in this area, well, axis 16 and 13, it's very clear now that we don't need. So basically, we have this reverse camera up there, camera 3, and that's how this reverse is driving right now and reversing all the scene, including
I
objects
think that was the good. Yeah, exactly. That's what
and the
Salvador asked.
and the
Well,
camera and the
if I
camera.
would do it again like that, sorry, what am I doing? That. Yeah. So, and even if the camera, we can actually supply the camera over here as well, then theoretically, the entire scene would be now kind of like reversed to be in the
Exactly
right
to the
place, right? That's the thing.
yeah.
This was actually just to demonstrate that basically what we're
Mm-hmm.
doing
Yeah.
is just to reverse. We're basically moving the entire thing in relation to the camera,
Mm-hmm.
which is exactly how a rasterizer works.
Yeah.
Okay, it's reverse everything to the camera, cancel the camera, then we can actually render everything in relation to that. So anything else?
No,
Cool.
pretty clear. Pretty clear.
Okay.
Thanks.
So what I want to show is basically we can do something similar, and that's what I told you about like how to. I'm just going to kind of a bit expand on that. What's that time? Sorry, yeah, okay. So then I wanted to expand a bit on that, and then I said, okay, let's try to take this result, and I'll do it in a bit of a different way as well to show you just another way to still do it. Okay. So I'll take this X over here, and I'll just put it over here. So I have the reverse camera and axis, right? And my axis, original axis over here. And I took this, just basically just 1 pixel. I think it's actually more, but let's say it's 1 pixel over here. Okay. And I'll basically put this value over here in the image. I'll put the global value over here. I'll take this X, Y, and Z. Okay, so now basically literally just copy from the wall matrix column into this guy X, Y, and Z over here. Actually, let me just copy so you can actually see what I'm doing. I'll just copy it. I think it's going to help a bit. To do what we can. On. What is it? Value. So, okay. Showing something?
No, it will be just value in this case. Value error.
But it doesn't. Yeah, it is R. I think it's just not updating. Okay.
No. It's supposed to be instead of nope. I think you should put value. So instead of nope, we're writing just value.
No. There it is. I think it was just an error.
Okay.
Because we want to actually value will give you the result, this result. I want to show the expression. So not actually show the expression inside. So I'll do it like that so we can actually see it. So basically I'm literally just copying the metrics, right? I'm just telling it copy the metrics. It's supposed to be like that. Yeah. So I'm literally just copying the metrics into the color. Okay. So now I'm literally plotting the color of where the axis is, right? I'm just translating X, Y, Z into RGB. So that's what I'm doing over here. I also have the camera. And what I would say is that, let's say I kind of like skim over it. I'll just go a bit slightly more in depth so you can actually see how point render works. But basically all we're doing is I'm going to do the same thing, but instead of actually doing it over here in a translated translation node, it's kind of like this expression. I'm going to do it with just regular nodes on the image itself. And then we're going to plot it. We're going to put it on the screen itself. Okay? And the way I'm going to plot it, not going to explain much about it. It's with blink. But with blink, I can just tell him, look at this value over here, this pixel, look at those values, and then go to this basically pixel on the screen. So once we're going to finish converting into the right screen space values, we're going to be like, let's say 200 on 300. It will go to that pixel and just put one pixel of white over there. That's all it's doing. Okay, that's our tool. So to do that, we said basically our order is like that. First, we have to go and put it over here. So we have this value. First of all, we have to divide our Z with X and Y. So to do it in the image wall, we have to basically do the red, which is the X in this case, divided with the B. Green is the B as well, but we have to do it in minus, right? So this corresponds to basically us doing X divided by Z and Y divided by Z. So those first section is exactly, it's exactly that. So this node over here on the image is just doing this part, right? That's all it's doing. Then we're multiplying this ratio, the length ratio, which is basically the focal over aperture. We're just multiplying the value on the image, multiplying. Then we're multiplying our resolution. Okay, so I'm just multiplying. Great. And then I'm going to do the offset, which is, we said it's basically half and half. Again, I'm just doing it to the image. So once we've done all this operation on the image itself, we actually got new value. I don't know if you can see it over here, it's too small, but basically the value is like 790 and almost 1000. Basically, this is where it's supposed to sit in the image. And if I'll take my tool that I'm just saying, take this pixel and literally just put a pixel over there, I will get a pixel over there. So if I'll measure over here, it literally put a pixel in 790 pixel and almost 1000 pixels. So it's actually put for us a pixel over there. And if I'll put it on our image, it's exactly where our image X is supposed to be. So if I'll do it a bit like that, should do it like, I can a bit more. Yeah. And if I let it drive it, basically we did exactly the same thing. But instead of just a reconcile, we just put it on the screen. That's basically what we did. Is a very basic thing, and it works for us. And then we can expand on this idea and say, okay, we don't actually need, we can do much more just one pixel. What if we'll just take a lot of pixel, random pixel, and do the same equation again? And exactly this is how renderer works, Rasterize works. It's just going to take every value of every vertex and put it into the screen. So if I'll, in this case actually, I took this kind of like array of colors, as you can see, and they're actually representing kind of like the equation of a circle. It doesn't really matter how I done it, but basically that's what it is. Rotating it with the same axis. So now I'm doing the same thing. I'm rotating the value with the color matrix to actually get the same result over here. And if you look over here, now we have a ring of them surrounding our sphere, right? And this is still working for us. So now we actually move from 1 pixel into actually all this ring. And actually, if I'll go and change the resolution of our input, means I'm actually adding more and more pixel, we'll get more and more points, right? I can put 100 and I have like 100 now points that actually go to the same equation and just putting for us this ring around our sphere. And this is, of course, expand to, of course, see where it goes. If I'll just feed in some just noise into the RGB, I'll get something like basically like that. And this is basically becoming what we, of course, know as point render, but any basically particle render works in the same way, where I'm just having an input of this noise value, which is tied to the X and Y and Z, and doing exactly the same equation as before. Is there any question about that? Is it perfectly clear? Everybody's on top and cool? Cool.
Oh, good. Thanks.
I just want to show you a small trick that you can also do. If we have a particle system, it's quite slow nuke. So I have this kind of like particle system over here. A lot of time, the drawing of it is actually slower than just running simulation. So you have a hidden plugin if you go over here and do all plugin and update, it will take a second. Then you can actually see all the plugins that you have, even the hidden one that you cannot just see on the regular basis. And there is a tool over here called particles to image. And this will export every particle position, but as a pixel. So this specific particle and this particle, all of them now are actually being drawn like that. So this image, if I open it over here, it actually tells us, right? The position now is going to be exported in the RGB. So now I have this image that each pixel over here is again X, Y, Z. It's exactly as we did over here before. It's the same thing, same trick, right? So now instead of actually just putting a noise, I can again do the same thing. I'll just drive it to the same system. And now I have the same result, as you can see. And if I'm driving that, it's exactly the same thing. But I think the benefit of that is that this is way faster than actually scanline render. So if I'll go over here and I'll ask the particle emitter to be, I don't know, let's say 100, 1000, and I'm also have kind of like particle steps. It's actually times 5, and that would actually work pretty fast as well for us. And you can actually, I've done tests in the past, actually can really accommodate like 1 million or something. Like if you actually really have a heavy thing, and you can say actually what's really slow for him. I mean, in particle system is actually quite slow regardless to that because of the 3D system. But on top of it, also rendering that's even heavier. So now actually we can just render our own particle system quite easily. And we can of course put a camera and of course rotate it and do everything we need to do. It's the same thing. And we can also drive the color like before. And from here we can think about kind of like different sampling, not just one pixel or whatever we need, right? And just as an example, we can of course, like the particle system, we can shuffle different expressions. So I have an image over here and I'm just running a sine kind of like wave on it, doesn't matter. And we have this kind of like very cool and kind of like running thing kind of like in the wave. So it's just kind of like an example of what we can do, of course, with it. And I'm sure you've seen it before with particle render and stuff like that. But it's just to show you how we can build so many things on top of that, right? And with the idea. So if there is no more question, I'll park this one and we'll go to the second part of what we wanted to do, which is going to be anyway shorter. Is there any
Sorry.
question? Yeah.
Yeah, I was a little bit lost with the particle example.
This one, this guy?
Yes. Yeah, just because we don't have any camera here, so I was a little. So
okay,
we are reaching it. We are at the origin of the axis, right?
No, so you're absolutely right. If you're absolutely right. If I had the origin, actually, we'll see it like that. See, I actually do have an axis. We'll actually see it like that because actually we're seeing some particles here. I don't know if you can see the screen.
Yeah.
But they are kind of like a mess. So I do have an axis over here, and I'll use that as my camera. Okay. So this is actually rotating for us everything. And I have basically, we don't have to use my thing. We can, if you don't know how to do it, you can actually just use a camera matrix over here. Okay. Mm-hmm. This will drive your rotation. If I'll go, so as before, to drive the camera, we'll have to take those last column over here. Yeah. In the workshop of the matrix, I explained that this 3x3 is everything else, is the orientation. So if you copy this 3x3 into the camera matrix over here, and then if you put an add, because it's translation, into the left column, we're actually doing the same thing. And now basically we have a camera system without any expression, okay? Mm-hmm. So if I'll take this one over here, it's the same thing as my expression, exactly the same thing. And that will actually drive my scene. So now I can actually use the camera and I can move it around and I can rotate and yeah, that's my camera. Otherwise it would not work as well. Sorry, I should have mentioned this.
No problem. I mean, it's amazing.
Cool. So any other question that is not clear on that?
Maybe I have one. Not sure if it will be like a 100% correlated, but you know, in terms of particles, can you gather like existing cache particles from a 3D software and be able to modify P-scale in Nuke somehow with this setup? So not using the within like a built-in particle simulation system from Nuke, but actually modify existing particle cache either coming from USD and or from Alembic.
You can write your own. I mean, I don't know if it's possible. I'm sure it's possible. You probably have to write a tool. I wrote in the book as well tool. That's how I've said things. our rally tools can actually convert different kind of like input data into an image, exactly like that, and then actually drop it into my own system as well. I have my own, actually I have my own tool for that as well. And it's called Starfield, and it's exactly, it's kind of like a particle renderer. But you can actually drive it inside, you can actually let any image drive it basically. So if you can read build your own kind of like reader into an image system, your cache or whatever, then you can do the same thing. I don't know if it helps you, but there is no, as far as I know, there is no tool right now to do it directly. Maybe they build it in the future. I think actually there is particles for Blink, right? There is Blink for particles. So I'm thinking that maybe with that.
Mm-hmm.
So there is a directive. You can write one that can convert this one, and then you can actually let it drive the system. I don't know if it helps you, but yeah.
Okay.
Cool. Yeah. Maybe in the future I'll go back to that. But yeah. Fine.
Looking forward.
Cool. If all that kind of like makes sense, now I want to take the time we have to do the reverse thing. This is a bit more advanced mathematically, so I won't fully go into the future of that. I will just try to explain the intuition of that. But essentially, the problem is reversed, right? So now we have essentially kind of like an image that we got from, I don't know, we have a camera tracking in, and we have this beautiful thinnable shot, as you can see. It's clearly definitely very realistic. And we want to do the reverse thing. We want to have an axis over here, or a point in space, right? The opposite of Reconcile. And I want to find it in 3D space, where it actually sits with the object. That's what we actually want to do now. And essentially, it's very easy. It's very easy. The first step to do is reverse everything that we've done, right? So we have to reverse the resolution thing that we've done, the focal length ratio thing that we've done. Let's do it now actually quite quickly. So let's say we have, actually using this one, I have this one over here, right? And to reverse it, I don't know if it's already doing that. I don't think it is. We don't actually need it. It was an example actually to see how it is. First of all, the first thing we have to notice is that we don't have Z component anymore. This image is 2D, of course. We lost one dimension, and we will not be able to recover it just like that. We have to have another information on that. So our first step is to first of all see if we can actually convert it into the 3D space, but put it in the -1 image plane, right? Basically from the camera and kind of like -1 image plane. So our goal is actually to put it exactly in front of the camera, but in the same location as the 2D axis would actually sit. And to do that, I think I already done it over here. Probably done it over here. Yeah. We can, I think I tried to show that we can actually do it again with the offset. Is this the offset before? We can probably do the same trick as before. Like if I'll go over here and put the offset over here and 1-on-1, this would actually put our element again. Basically, it aligns the origin and the image again at the 0, 0. Now I'm a bit. One second. Sorry, 1 second. So basically, I wanted the same trick as before. I wanted to kind of like cancel the offset as before we've done, because I think it's a bit confusing for Alexa, okay? Yeah. So basically, I just wanted to have to cancel the offset, but I just want to be sure that we're going to do the same thing. We're going to try to put the axis in front of it. And the first thing we talked about is basically we have to have this kind of like, we have to have a scaling factor. So before we multiplied with the resolution, with the f of v, now we're going to divide with it. So first of all, I'm going to link our axis and translate x, translate y. I'm going to just copy it into the axis world, okay? And clearly it doesn't make any sense because now it's actually somewhere over here because the units are crazy, right? So the first thing we have to do is, of course, divide it with width. And that. And our height. Sorry, actually twice with it, with no height over here. Okay. And that basically gives us something that is basically over here. So it's kind of slightly closer. Now, I mentioned before that you cannot just use width and height in the axis over here wall, because if I'll do it over here, I don't know if you can see it on the screen, the width is actually the resolution of 640. It doesn't pick up the format resolution on the input. You have to be explicit with it. So to do that, I actually created a knob over here that has resolution and offset. So I can actually always put the right values here. Okay, I don't know if actually you can see it. Again, if I write over here in the equation, if I write width, it actually gives me the value now, right? I have to do out the value, I assume. Yeah. Right, so if I literally use the width, I will get this value, which doesn't correlate to anything in our script. Not the input of this guy, not the input of this guy, not the thing. So we cannot just write width. So instead, I'm going to put these kind of like knobs over here and use them instead. So now I'm going to do, instead of width, I'm going to do red. This is the name of my knob. Okay. And now it's set to make a bit more sense. Great, so now it's actually also closer. And the second thing is, of course, we have the focal thing that we had before, right? We have to take into account of that. So now let's divide with this one as well. I'm literally reversing the order as before. That's all I'm doing. I'm dividing length ratio. It's not length ratio, is it length? Sorry, it's a typo. It's length ratio for some reason. And I'll do this one. Live ratio as well. Yeah. And this is, of course, correspond to our offsets before. Yeah. So as we have that, let's put it like that. It's in the image. We have this guy. So we actually now select the actually line. We just literally just reverse the order of the multiplication we've done before. Now we're dividing with the resolution size, and we're dividing with the focal lengths we've done, ratios that we had from before. So it's exactly reversing the order. So as you can see in our previous one, we did multiply resolution, multiply ratio. Now, instead of multiply, just doing divide over here. And we can see that already it's aligned for us with the axis. Okay, so now that now are basically both kind of like aligned to what we need. I'm ignore the animation that we have over here, but now they're both aligned for us. Now, the thing that I've done over here is in order to cancel the camera movement, you would have to actually do something like that. This is our axis. We're doing this translation thing, and we have to actually concatenate to the camera. This will now put our axis exactly in the right ratio from the camera in 1 unit away. So if I look from the camera, and actually now I can see the offset. Actually, sorry, I'm jumping ahead of myself. Let's now add the offset as well to see how it's working, and then I'm actually going to show you how it actually looks like. So in order to do that, let's have this. Yep. Let's put it like that. And put it again in the same place. And I'm going to cancel the offset that we had over here. Have an axis. Translate. And of course now we have to have the offset as well as before. But we have to remember that the offset is actually coming over here, basically on the Y. So I will do offset. And again, like before, I had to do offset over here on the side. I cannot just use any width divided by half, because then it will get skewed again. So I'm doing it again the same over here. And I'll zoom in on the equation so you can actually see it pretty clearly for you guys. You can see what I'm doing properly. Like that. What have I done? And I'm still missing something. What am I missing? What am I missing over here? Anybody can tell me what am I missing? over here. Yeah, let's see what I missed because I probably retyped something incorrectly. If I copy the value of the, you can say exactly my equation, which is nub, and then trans x. Yeah. Okay. So I just want to show that this is exactly what I'm doing in each component. I'm taking the translation x, I'm offsetting that with half of our resolution. And then I'm doing the reverse again. I'm just dividing with the resolution and then dividing with the ratio. This gives us exactly an axis that sits on the -1 image plane, right? It's basically a vector, right? Basically point from the center of the camera in a direction of where the 2D is basically aligned. And if you look at the 3D world, you can see it's over here, right? So if you look from the camera view, we can actually see exactly where it is. So it's 1 unit away. It's aligned with what we need. It's aligned with what we need, right? And it's 1 unit away from the camera. So I know I kind of like did it too quickly, but does it make sense what I just did basically? I'm just going to basically reverse the order. Anybody?
Yeah.
No? All good?
Yeah.
Good. The reason that I'm doing that is because now we still need to find this point over here, right? This point where it corresponds to the 3D system, right? So in order to do that, so first of all, let's do something like that. So first of all, I'll try to draw a line of where it goes from the center of the camera and our axis that is corresponding to the 2D world, right, in the image plane. And if I'll draw a line, basically we have a ray, an infinite ray, right? And goes to infinity, and it does actually cross our sphere. So we know that basically the point we need is somewhere along this guy, right? That's what it is. So if we look, of course, only from this point of view, it's not enough, right? Because we don't have the Z. What we need is another image that we can actually triangulate between them. So what I've done is actually put another camera in a different position. So our first frame is like that, our second position is like that, okay? And it also shifted a bit. So if we look over it from here, I'll just show this guy actually, so you can see that. We have 2 points now, from the beginning and in the end. Okay, I just did an animation thing. And now we can see that basically our array is being moved over here, and we can actually see it exactly how it's moving. And cut-to-tract, tools like cut-to-tract, works in that way, basically, that you look from a different angle, and you put this kind of like scale factor to see how much the array should actually grow. So in this case, what I have over here is I have this axis over here. How come this? Sorry, yes, of course. And this X, I think, already is taking the animation on the other guy. So what I'll do is like that. So this guy over here is actually picking up the keyframe of the other frame. So what I've done, I'll just use the first frame. So it won't matter what we've done. And if I go over here, we still have this guy over here, right? It sits over here. And now we have the scaling factor, right? If I go over here, sorry, it's this guy, as you can see. This is what it is. And now I have a scaling factor. So if I go and scale that guy to some certain value, right, it will exactly move on this ray. And at some point, it will cross where we need to do. And that's exactly what cut-to-tract is doing. As we're moving from this point of view, and I'm not sure why we're not seeing that. Yeah, okay, there it is. As you can see, as I'm scaling this guy up, now it's actually outside of a screen because it's actually crossing the other camera, right? Probably the one is somewhere over there. So our camera is actually sitting probably over there in relation to where we are right now. And as I'm scaling it up, it will align to somewhere over here. And basically cut-to-tract and other tools would ask you to kind of like zoom in, to kind of like find exactly the right scale. And this scale just tells us basically if we scale our original vector by this amount, we'll get a new point in space. And this is exactly where this point is in 3D world. That's how we do it. Now, I actually want to show you as well on this guy because I think it's going to make sense as well over here. Is it this one? just kind of like pushing the ray, right? That's exactly what we're doing. It's just pushing the ray until it aligns with what we need. And then we'll use this kind of like scale factor to drive everything else. Does that make sense, roughly? I know I kind of like skimmed over it, but it makes sense? Cool. So the last point that I will just say on that, yeah? Do you want to ask anything? Okay. So the last one I want to say is clearly this is a bit kind of like manual labor. I wanted just to show that we can also do it in a bit more advanced way. So I'll just take 5 more minutes if it's okay with your time. And just kind of the last piece of the puzzle. I'm not fully going to go into that's why I meant that it's a bit complex. All these parties, I think, should make sense because we're just reversing everything here. And then we're kind of like looking at kind of like this image theme of triangulation. When I'm saying triangulation, I mean that basically we have a camera somewhere over here and it sends the ray like that. Then we have another camera in different frames and maybe the ray is over here. And the intersection between them is exactly where our 3D point sits. And before what we did is we manually looked for a scale finder. We just walked on this array until we find it's actually where it intersects with us. That was done manually. We can also do it automatically, or basically we can actually solve this equation to find this point automatically. And I'm not going to go fully into it because I think it's a bit kind of like confusing for us in this state. So again, I have this kind of like 2 points. I have this kind of like 2 points over here. And I have something that actually looks like that. I don't want to scare you. It's literally just converted everything. It's kind of like 2 rays. It's basically those V1, V2, and base 1 is literally just saying this is a vector, this is vector 1, this is vector 2, and we have this line, it's another vector, let's call it the base between the 2 camera, and it triangulates exactly the solution of where those 2 intersect. So this is kind of like, and this is what this equation is doing. It's finding the intersection of this thing by triangulating them. And I don't know if you can see, there is T1 and T2 over here. This is the scale factor that we wanted from before. But instead of doing it manually, we just use this equation to solve that. And when we have that, actually we do get, so now we have this ray thing. I think I have to probably open this one. This one. Okay, I forgot which one is which anymore. It's too many. Yeah, I don't know if you can see it. I'll do it maybe like that. No, I cannot see it like that. I'll do it like that. Okay. I don't think you can see it, but there is a point over here that it gives me exactly the intersection of what we need. The last piece of the puzzle that we don't have time to go into as well is, and this is just an inspiration like the particle system, is that of course we can do something more advanced. Instead of actually still going manually by that, if we look at the result over here of our first frame, so now we have basically 2 frames, right? We have 1 and 2. If we look at the vector, so if we basically go to the scanner random and we have the vectors over here, so motion vectors, and we'll look just at the vectors, those values literally tells us how much every polygon moves in screen space between each frames, right? So if I'll go and sample a point over here in space, right, the values over here tell me that in the next frame, this is how much it's actually shifted, right? And this is how we do basically motion blur, vector motion blur and stuff like that. So what if we'll just use that to drive our point or to find a point? So what I've done just to show the point is that we have 2 frames, right? First frame and second frame, right? This is our second frame. I'm going to just circle what we actually want to find. I'll shuffle into it the motion vector and I'll distort it. As you can see now, this is the first frame. Sorry, this is the first frame and this is the second frame. Now it's actually aligned exactly, right? So we know the values over there are exactly correspond to that. So I can actually use those values to drive our equation to find the point. But we can do something more than that. Instead of just finding 1 point, what if we just do it for every pixel, right? If I look at this result and just, let's say, stand over here, right? Standing over here gives me a position in screen space, okay? Looking at the values over here tells me that this pixel is going to jump, in this case, minus 200 pixels to the left, okay? So I can actually even do that. Let's say I'm going to stand over here. This position is over here. I'll just do it like that. I'm going to do, this pixel is actually over here. I'm literally copying the value from below. Now I have this guy, and I'm going to put in the translation the value of exactly the velocity. So like that. Sorry. Like 10. And as you can see, it actually jumped over here now. And if we look over here on this, and I probably ruined something as usual. I don't know what I've ruined. You should trust me, it's actually worked before, but I think what I've done before, yeah, I probably ruined something, but it actually works for us. I didn't sample the right pixel, sorry, I should have sampled the right pixel, but actually it translates. If we do the entire thing, I have a tool that actually does it for every pixel, this equation. It's actually literally translate this data with the camera into actually p-world. So if we'll take this guy and apply it as pixels, we actually get, again, the scene. And this is not, I don't use any p-world. There is no position path. I literally only use a velocity and a camera to reconstruct the scene. So I'm kind of like extending on trying to find a point in space, but now for every pixel. And we don't really only need to use velocity. We can also just use basically an overflow for that if we have basically 2 different frames and a camera to sort of reconstruct our scene. I know I rushed into it and we are way over time. And I probably confused more of you, but this is just an inspirational thing, just to show the point. Again, this is not my polygon. This is literally me reconstructing the scene with an overflow. And extended on the idea of basically how to find a point in space. Does that confuse everybody and everybody's kind of like really lost as well?
Yes.
Okay.
Mission accomplished.
Yeah.
Mission accomplished.
Yeah. But
any questions for like 1 minute of question if you want to ask?
Too many.
Yeah.
Too many.
But we will save the script, I guess. That will be very helpful.
But I just want to know, does this make sense? Like what we did over here, that we have basically 2 cameras, 2 rays, and we find intersection point. Did this make sense? Even in a scale factor thing, this makes sense, right? I didn't explain how we did it mathematically, but we're just projecting 2 vectors to one another. I'll say that in the real world, there is no intersection point, by the way, because of noise and different things. So what we're actually doing is finding the shortest path between those 2 lines, between those 2 rays. Because if I'll zoom enough between them, you can actually say they're not really intersecting, they're slightly one above the other because of noise and how it actually works. So we actually use an equation that's actually literally called find the shortest path between 2 lines. And it actually gives us that. And this point is the intersection point of what we need. And I actually extended to do it for each pixel. Right? That's what I've done basically. I created 2 rays for each pixel with the camera, and it actually gave me exactly point on all of them. So, okay. Nicola, it's too late, but thank you. It just gave me 2 frames and a camera, but I think it's too late to explain. I think you're probably over it. But if you guys understand up until here, then I'm happy. It's okay. If you guys understand how we kind of like find it, again, the point over here in the image plane, and then we just kind of like do the scale thing, that's okay as well. This is just, again, like the particle system, just extending the idea that we can actually do more than that. It's just different edge cases on that. If we have any time in the future, I can reiterate this concept and what I've done and maybe bring a real world example, because actually I use it in production as well. But for now, yeah.
Cool.
Small questions? No, nothing? Everything is clear, perfectly fine, right?
Yep. All right. Guys, let's go to our meetings. We have to jump to morning.
Have a good one.
Thank you very much.
See you next time.
Thank you.
Thanks. Ciao, ciao.
Thank you.
Bye.
Thank you.
Okay, FL. Recording.